What we know about dark matter and dark energy. In 1933, Swiss astronomer Fritz Zwicky made a groundbreaking observation while studying the Coma cluster of galaxies. He noticed that the visible matter within the cluster was insufficient to account for the gravitational forces holding it together. This missing mass problem led him to propose the existence of dark matter, an unseen substance providing the necessary gravitational pull. Zwicky's observations laid the foundation for one of the most significant mysteries in astrophysics, sparking decades of research into this elusive form of matter. The next major milestone came decades later in 1998, when two independent research teams studying distant Type Ia supernovae made a surprising discovery. They found that these supernovae appeared dimmer than expected, suggesting that the universe's expansion was accelerating rather than slowing down. This revelation introduced the concept of dark energy, a mysterious force driving this accelerated expansion, profoundly altering our understanding of the cosmos. Dark matter and dark energy together account for about 95% of the universe's total mass and energy. Despite their dominance, they remain undetectable through conventional methods, as they neither emit nor absorb light. Instead, their presence is inferred through their gravitational effects on visible matter, radiation, and the structure of the universe. This makes them central to modern cosmology, posing challenges that continue to defy direct detection and comprehensive explanation. The evidence for dark matter is compelling, particularly in galaxy rotation curves. Observations show that stars in the outer regions of galaxies orbit faster than they should if only visible matter were present. This discrepancy suggests the presence of an invisible halo of dark matter exerting additional gravitational force, providing a key clue to its existence. Dark energy, on the other hand, is studied through its influence on large-scale cosmic structures. Observations of the cosmic microwave background, CMB, a relic of the early universe, reveal detailed patterns that align with the presence of dark energy. These patterns also confirm that dark energy constitutes roughly 68% of the universe's total energy density, emphasizing its significant role in shaping the cosmos. The discovery of these phenomena has led to the development of advanced theoretical models, such as the lambda cold dark matter, lambda CDM, model. This framework combines dark matter, dark energy, and standard physics to describe the universe's evolution and structure. It has become the cornerstone of modern cosmology, offering insights while also highlighting the limitations of our current understanding. Despite its success, the lambda CDM model raises new questions. For instance, what exactly is the nature of dark matter particles? Candidates like weakly interacting massive particles, WIMPs, axions, and sterile neutrinos have been proposed, but none have been conclusively detected. Similarly, dark energy is often associated with Einstein's cosmological constant, yet its origin and properties remain deeply mysterious. Experiments like the Large Hadron Collider, LHC, and underground detectors such as Xenon 1T aim to uncover evidence of dark matter particles. These efforts represent a global scientific collaboration to unlock the secrets of the universe. Meanwhile, space missions like the Euclid and Nancy Grace Roman telescopes focus on mapping dark energy's influence on the cosmos. The interplay between dark matter and dark energy is also a subject of intense study. While dark matter's gravitational pull helps form galaxies and clusters, dark energy counteracts this by driving the universe's expansion. Understanding how these opposing forces have shaped cosmic evolution is crucial to unraveling their mysteries. The 1998 discovery of the universe's accelerated expansion marked a paradigm shift in astrophysics. It demonstrated that our understanding of gravity, based on Einstein's general relativity, might be incomplete when applied to the largest scales. This has prompted researchers to explore modifications to existing theories, opening new avenues of inquiry. Dark matter and dark energy also challenged the boundaries of experimental physics. Their elusive nature requires innovative techniques and technologies to probe their properties. From advanced particle detectors to next-generation space telescopes, the quest to understand these forces drives technological innovation and interdisciplinary collaboration. While dark matter and dark energy are often studied separately, some theories propose they might be interconnected. Speculative ideas suggest they could be manifestations of a single underlying phenomenon or linked through mechanisms not yet understood. Such hypotheses highlight the profound gaps in our knowledge and the potential for revolutionary discoveries. The influence of dark matter and dark energy extends beyond science, shaping philosophical debates about the nature of reality. They compel us to question the limits of human perception and the tools we use to explore the universe. As unseen forces dominating the cosmos, they embody the mystery and wonder inherent in scientific discovery. Despite the challenges, the study of dark matter and dark energy exemplifies humanity's drive to understand the unknown. Each new observation and experiment brings us closer to unveiling the secrets of the universe, inspiring future generations of scientists. The timeline of discoveries, from Zwicky's observations in 1933 to the accelerated expansion revelation in 1998, underscores the evolving nature of scientific inquiry. It reminds us that the pursuit of knowledge is a continuous journey, with each answer leading to new and deeper questions about the cosmos. Dark matter, the cosmic scaffold. Role and structure formation. Dark matter plays a fundamental role in the formation of cosmic structures. In the early universe, shortly after the Big Bang, small fluctuations in the density of matter created regions with slightly higher gravitational pull. Dark matter, with its significant mass and gravitational influence, began to accumulate in these regions, forming the seeds of what would eventually become galaxies and larger cosmic structures. Without dark matter, the observable universe as we know it would not exist in its current form. The gravitational pull of dark matter allowed ordinary matter, primarily hydrogen and helium, to clump together in the dense regions of the early universe. This process led to the formation of stars and galaxies. Dark matter acted as a cosmic scaffold, providing the necessary structure for these processes to occur. Its influence extends to the large-scale distribution of galaxies, forming a vast cosmic web that spans the universe. One of the leading hypotheses about dark matter is that it consists of cold dark matter, CDM. CDM refers to slow-moving, non-relativistic particles that interact only weakly with ordinary matter and radiation. This model aligns well with observations of galaxy formation and the large-scale structure of the universe, making it the most widely accepted explanation for dark matter. In contrast, warm dark matter, WDM, and hot dark matter, HDM, are alternative models that propose faster-moving particles. WDM consists of particles with moderate velocities, while HDM involves relativistic particles moving at near light speeds. However, these models face challenges in explaining the observed distribution of galaxies and the detailed structure of the cosmic web, making them less favored than the CDM model. Observations of the cosmic microwave background, CMB, have provided critical evidence supporting the role of dark matter in structure formation. The tiny temperature fluctuations in the CMB correspond to density variations in the early universe. These variations grew over time, guided by the gravitational influence of dark matter, to form the galaxies and clusters we observe today. The role of dark matter extends to galaxy rotation curves, which offer direct evidence of its presence. Stars at the edges of galaxies orbit faster than can be accounted for by visible matter alone. This discrepancy points to a halo of dark matter surrounding galaxies, providing the additional gravitational pull needed to explain the observed rotation speeds. Dark matter also influences galaxy clusters, the largest gravitationally bound structures in the universe. The mass of visible matter in clusters, including stars and gas, cannot account for their observed gravitational effects. Dark matter fills this gap, making up the majority of the mass in galaxy clusters and holding them together. Gravitational lensing is another phenomenon that reveals the presence of dark matter. When light from distant galaxies passes near massive objects like galaxy clusters, it bends due to gravity. The degree of bending often exceeds what visible matter can produce, indicating the presence of unseen dark matter. The nature of dark matter particles remains one of the greatest mysteries in physics. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, sterile neutrinos, and axions. Each candidate has unique properties and interactions, but none have been definitively detected despite extensive experimental efforts. Underground detectors, such as the Xenon 1T experiment, are designed to search for dark matter particles through their rare interactions with ordinary matter. These experiments use highly sensitive equipment to detect the faint signals produced when dark matter particles collide with nuclei. In addition to direct detection efforts, indirect detection methods aim to observe the byproducts of dark matter annihilation or decay. These processes could produce gamma rays, neutrinos, or other particles detectable by specialized observatories. While intriguing signals have been observed, none have provided conclusive evidence of dark matter. Dark matter's influence is not limited to individual galaxies or clusters. It also affects the overall shape and dynamics of the universe. Cosmological simulations incorporating dark matter accurately reproduce the large-scale structure observed in the universe, lending further support to its existence. Despite its gravitational effects, dark matter interacts only weakly with ordinary matter and radiation, making it incredibly challenging to study. Its elusive nature has prompted the development of innovative technologies and experimental techniques, driving progress in both theoretical and experimental physics. The interplay between dark matter and ordinary matter continues to be a topic of intense research. Understanding this relationship is crucial for unraveling the mysteries of the universe's composition and evolution. As scientists probe deeper into the nature of dark matter, they hope to uncover clues that could transform our understanding of the cosmos. The role of dark matter as a cosmic scaffold underscores its importance in shaping the universe. From the formation of the first galaxies to the large-scale structure we observe today, dark matter has been a driving force in cosmic evolution. Its study not only addresses fundamental questions about the universe but also inspires the pursuit of knowledge across scientific disciplines. Dark energy's effects on the universe. Cosmic expansion? Dark energy, a mysterious force that permeates the universe, has profound effects on the cosmic landscape. It is believed to be responsible for the accelerated expansion of the universe. While gravity pulls matter together, dark energy works in the opposite direction, pushing galaxies apart. This imbalance between the forces of attraction and repulsion is causing the universe to expand at an ever-increasing rate. The expansion itself is not uniform. Some regions of space are stretching faster than others, and this effect is most pronounced on the largest cosmic scales, where dark energy's influence becomes more noticeable. The implications of dark energy on the future of the universe are still debated among scientists. One possible outcome is the Big Rip, a scenario in which dark energy continues to intensify over time. As the strength of dark energy increases, it will eventually overpower the gravitational forces holding galaxies, stars, planets, and even atoms together. In this scenario, galaxies will be torn apart, stars will be pulled from their orbits, and eventually, the very fabric of matter will be ripped apart. The Big Rip is a chilling possibility that suggests a future where everything in the universe is disintegrated into its fundamental components. Alternatively, the universe might experience a big freeze. In this model, the expansion of the universe continues indefinitely at a decelerating pace, but never actually slows down or reverses. As the universe grows, stars burn out and galaxies drift farther apart. The universe would gradually become colder and more desolate, with distant galaxies becoming unreachable as their light fades away. This scenario could lead to a state where the universe is cold, dark, and essentially empty, with no new stars forming and no interactions between distant objects. Another possible end is the Big Crunch or Big Bounce. In this scenario, dark energy's influence diminishes over time, and gravity regains its dominance. Over billions of years, gravity could gradually slow the expansion of the universe, eventually causing it to collapse in on itself. Galaxies, stars, and planets would all be pulled back together in a massive contraction, leading to a singularity where everything is crushed into an infinitely small point. This scenario might not represent the end of the universe, however. Some models suggest that the collapse could lead to a Big Bounce, in which the universe undergoes a cycle of expansion and contraction, potentially leading to a new cosmic epoch. The question of which of these outcomes will prevail depends heavily on the properties of dark energy. Current measurements suggest that dark energy is not only present but also increasing in strength, which would favor a Big Rip scenario. However, there are still many uncertainties surrounding the exact nature of dark energy and how it behaves on the largest scales. Some theories propose that dark energy could change over time, potentially leading to different cosmic fates. One important factor to consider is the amount of dark energy in the universe. While dark energy seems to make up around 68% of the universe's total energy content, its exact nature remains elusive. Theories about its properties range from a cosmological constant, a form of energy that remains constant throughout space and time, to more dynamic models where dark energy evolves. If dark energy remains constant, the universe could continue to expand forever. However, if it changes, the ultimate fate could be very different. The role of dark energy in cosmic evolution is also central to our understanding of the universe's past. The discovery of the accelerated expansion in the late 20th century challenged our understanding of gravity and led to the hypothesis of dark energy. Prior to this, cosmologists believed that the universe's expansion would slow down due to gravity. Instead, observations showed that galaxies were moving away from each other at an accelerating rate, suggesting the presence of an unknown force. This revelation has prompted a re-examination of the fundamental laws governing the cosmos. On the other hand, the eventual fate of the universe may not be entirely determined by dark energy. The interplay between dark energy and gravity could lead to unexpected outcomes. For instance, if dark energy weakens over time, gravity could cause the universe to slow its expansion and ultimately collapse. Conversely, if dark energy remains constant or strengthens, the universe could continue expanding forever, leading to a cold, dark, and empty future. Understanding these possibilities requires further study of both dark energy and the nature of gravity. In recent years, advancements in observational techniques have allowed scientists to gather more data on the expansion of the universe and the behavior of dark energy. Surveys of distant supernovae, the cosmic microwave background radiation, and large-scale galaxy surveys have provided crucial information about the universe's expansion rate and the distribution of dark energy. These observations are helping to refine our models of the universe's future and give us a better understanding of the role dark energy plays in shaping its evolution. The possibility of a big rip or a big freeze raises important philosophical and existential questions about the nature of life in the universe. If the universe continues expanding and eventually becomes a cold, dark place, it might signal the end of life as we know it. In such a scenario, civilizations would struggle to survive in an increasingly hostile environment, with no new stars to fuel their energy needs. The thought of a universe slowly fading into darkness raises profound questions about the meaning and purpose of existence on cosmic scales. As we continue to explore the mysteries of dark energy and the ultimate fate of the universe, it is clear that we are only beginning to scratch the surface of this vast and complex subject. The future of the universe depends on a multitude of factors, many of which are still unknown. Whether the universe will eventually tear itself apart in a big rip, freeze into an eternal void, or collapse in a big crunch remains one of the most exciting and unresolved questions in cosmology. What is certain is that the effects of dark energy will continue to shape the universe in ways we can only begin to understand. As our observational tools and theoretical models improve, we may gain more insights into the true nature of dark energy and its role in the grand cosmic story. Until then, the fate of the universe remains a tantalizing mystery, one that continues to capture the imagination of scientists and the public alike. One prominent approach to understanding dark matter and dark energy is through modified gravity theories. These theories challenge traditional models of gravity and suggest that the behavior of the cosmos might be explained without introducing new particles. One of the most well-known modified gravity theories is MOND, modified Newtonian dynamics. MOND posits that Newton's laws of motion and gravity, which work well in our solar system, might need to be adjusted on large cosmological scales. According to MOND, the gravitational force becomes stronger than predicted at low accelerations, explaining the anomalous motion of galaxies without invoking the presence of dark matter. This adjustment provides a potential explanation for the observed effects typically attributed to dark matter, such as the way galaxies rotate and the gravitational lensing effects seen in galaxy clusters. MOND does not rely on the existence of new particles like dark matter, but instead offers a modification to the fundamental laws of physics at large distances. While this theory has been successful in explaining certain galactic phenomena, it has faced criticism for not fully matching all the observed evidence, especially in more complex situations like galaxy clusters. Despite this, MOND remains a topic of debate in the scientific community, providing an intriguing alternative to the particle-based theories of dark matter. Another approach within modified gravity is the adjustment of Einstein's general theory of relativity to account for dark energy. General relativity, which has been highly successful in describing gravity and the behavior of space-time on large scales, might need to be modified to explain the accelerated expansion of the universe. The simplest solution to this problem is the introduction of dark energy, a hypothetical form of energy that fills space and drives the acceleration. However, some scientists have proposed that the equations of general relativity may need to be tweaked to account for this acceleration without invoking dark energy. These alternative theories aim to explain the cosmic acceleration by suggesting new forms of gravitational dynamics, such as adding additional fields or adjusting the behavior of spacetime at cosmological scales. One such theory is the FR gravity model, which modifies the Einstein-Hilbert action in general relativity. These modifications lead to new solutions for cosmic expansion and could potentially explain the observed acceleration without the need for dark energy. However, like MOND, these models face challenges when trying to explain all the observed phenomena consistently. The possibility of adjusting general relativity or proposing new gravitational laws is a fascinating avenue for future research, though much work remains before any of these theories can be conclusively proven. The multiverse theory provides another potential explanation for the phenomena we observe, particularly the mysterious nature of dark energy. According to the multiverse hypothesis, our universe is just one of many in a vast and potentially infinite collection of parallel universes. Each universe within the multiverse may have different physical constants, laws of physics, and even dimensions. In this framework, dark energy could be a byproduct of interactions between these universes, with each universe exerting some form of influence on others. These interactions could manifest as the accelerated expansion we observe, with dark energy being an effect of the gravitational or energy exchanges between universes. The concept of higher dimensions, closely linked to the multiverse hypothesis, proposes that the universe we perceive is just a three-dimensional slice of a higher dimensional reality. The extra dimensions could be compactified or hidden from our direct perception. Dark energy could then be a result of the interaction between our three-dimensional universe and these higher dimensions, where forces or energy states exist beyond our sensory experience. This theory draws on string theory, which suggests that the fundamental particles of nature are not point-like objects but rather tiny vibrating strings, and these strings exist in higher dimensional spaces. The manifestation of dark energy might thus be related to the geometry of these extra dimensions, altering the fabric of spacetime and contributing to cosmic acceleration. The holographic principle is another intriguing idea that has implications for dark energy and the nature of the universe. This principle suggests that all the information contained in our three-dimensional universe could be encoded on a two-dimensional boundary, similar to how a hologram works. In this view, the universe itself could be a projection of data encoded on a distant, lower-dimensional surface. Dark energy in this scenario could arise from the dynamics of this boundary or the encoding of the universe's energy states. It suggests that the universe's large-scale structure, including the acceleration of cosmic expansion, might be an artifact of the way our universe is encoded in a higher dimensional space, potentially altering our understanding of energy and gravity. As we explore the interactions between dark energy and dark matter, another theory that emerges is the possibility that dark matter might have its own forces, distinct from the four fundamental forces we are familiar with: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. This idea challenges the current understanding that dark matter is simply a non-interacting form of matter that only influences the universe through gravity. Instead, it suggests that dark matter might have an unknown interaction, similar to how electromagnetism interacts with ordinary matter. If dark matter does have its own forces, this could lead to new ways of understanding how galaxies and clusters of galaxies behave. For example, dark matter could have an electromagnetic-like force, which would affect the way it interacts with regular matter. This hypothesis could explain some of the more unusual behaviors observed in galaxy clusters, such as the missing mass problem, where the gravitational effects of dark matter are much stronger than predicted by visible matter alone. If dark matter interacts through some novel force, it might not just be a passive entity, but an active player in the formation and evolution of cosmic structures. This idea opens the door to the possibility of discovering entirely new fundamental forces. If dark matter interacts with regular matter through an unknown force, it could be detected through experiments that explore the effects of this force on ordinary matter. Some researchers have even speculated that dark matter might exhibit an electromagnetic interaction, but with much weaker strength than the known electromagnetic force. This could explain the difficulty in detecting dark matter directly, as it would not produce the usual electromagnetic radiation that we use to detect ordinary matter. There are also theories that propose that dark matter might be composed of exotic particles that interact in unusual ways. These particles might not only interact with gravity but also with one another through unknown forces, perhaps giving rise to new types of interactions that are not yet understood. These exotic particles could hold the key to understanding not just dark matter but the very nature of the universe itself. The hypothesis that dark matter could interact through its own forces also raises questions about the nature of the standard model of particle physics. If dark matter possesses novel forces, this could indicate the need for a new theory beyond the standard model, potentially leading to the discovery of new particles, forces, or interactions that could reshape our understanding of the universe at its most fundamental level. While the exact nature of dark energy and dark matter remains one of the greatest mysteries in modern physics, these theories provide exciting avenues for exploration. Whether modified gravity theories, the multiverse hypothesis, or new forces associated with dark matter, each approach offers a unique perspective on the cosmos and invites further investigation. The future of dark energy and dark matter research promises to challenge our fundamental understanding of the universe and reveal new dimensions of reality that are currently beyond our comprehension. Particle detectors and observatories play a crucial role in the search for dark matter and dark energy, helping scientists understand these mysterious forces. One of the most notable experiments in the search for dark matter is Xenon 1T, located deep underground in the Gran Sasso National Laboratory in Italy. This experiment is designed to detect weakly interacting massive particles, WIMPs, which are among the leading candidates for dark matter. The detector uses a large volume of liquid xenon, which acts as both a target and a detection medium. When a WIMP collides with a xenon nucleus, it produces tiny flashes of light and ionization that can be detected by sensitive sensors. The deep underground location is crucial because it shields the detector from cosmic rays and other background radiation that could interfere with the measurements. Xenon 1T has already provided valuable data in the search for dark matter. Although it has not yet detected any direct evidence of WIMPs, it has helped refine the sensitivity of future experiments by placing stringent limits on the properties of dark matter particles. This underground experiment is a key component of the global effort to detect dark matter, and its successor, the Xenon experiment, is expected to further improve the sensitivity and accuracy of these measurements. In addition to WIMPs, other particles that might help explain dark matter are being investigated using different methods. One such experiment is the IceCube Neutrino Observatory, located at the South Pole. IceCube is designed to detect high-energy neutrinos, subatomic particles that are notoriously difficult to detect. While neutrinos are not directly associated with dark matter, the search for sterile neutrinos, hypothetical particles that might be related to dark matter, has become an important focus of research. IceCube consists of a massive array of detectors embedded in the Antarctic ice sheet, allowing it to capture the interactions of neutrinos with the ice. By analyzing these interactions, scientists hope to uncover evidence of sterile neutrinos or other exotic particles that could contribute to our understanding of dark matter and the universe. The IceCube Neutrino Observatory has already made significant contributions to astrophysics by detecting high-energy neutrinos from distant cosmic events, such as supernovae and gamma-ray bursts. These findings have provided valuable insight into the behavior of high-energy particles in the universe. However, the search for dark matter-related particles remains a long-term goal for IceCube, and ongoing experiments are refining the detector's sensitivity to the elusive signatures of sterile neutrinos. Looking ahead, upcoming missions and telescopes promise to advance our understanding of dark energy and dark matter even further. One such mission is the Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s. This space-based observatory is specifically designed to map the effects of dark energy on the large-scale structure of the universe. By observing distant galaxies and measuring the way their light is distorted by dark energy, the Roman Space Telescope will provide critical data on the expansion rate of the universe and the role dark energy plays in this process. The Roman Space Telescope will use a technique called weak gravitational lensing to map the distribution of dark matter and dark energy across the universe. This technique relies on the fact that the gravity of large structures like galaxy clusters can bend the light from more distant galaxies. By studying these distortions, scientists can infer the presence and distribution of dark matter, as well as the effects of dark energy on cosmic expansion. The telescope will also conduct detailed surveys of exoplanets and star clusters, providing a wealth of data that will help answer fundamental questions about the nature of dark energy. Another groundbreaking facility is the Rubin Observatory, which is set to revolutionize our understanding of dark matter and dark energy when it becomes fully operational in the near future. Located in Chile, the Rubin Observatory will conduct a 10-year survey of the sky, collecting data on billions of galaxies and their movements. The observatory's flagship survey, known as the Legacy Survey of Space and Time (LSST), will provide a detailed map of the universe, capturing transient events like supernovae, asteroids, and gravitational wave sources. This survey will also play a key role in studying the effects of dark energy and dark matter on the universe. One of the main goals of the Rubin Observatory is to measure the impact of dark energy on the expansion of the universe. By tracking the positions and redshifts of galaxies, scientists will be able to observe how the universe's expansion rate has changed over time. The observatory will also search for clustering patterns in the distribution of galaxies that could reveal the presence of dark matter. These observations will help scientists test competing models of dark energy and refine our understanding of how it influences the large-scale structure of the universe. The Rubin Observatory will also be capable of detecting transient events, which could lead to important discoveries related to dark matter and dark energy. For example, the observatory may detect gravitational lensing caused by dark matter or identify supernovae whose brightness could be affected by the presence of dark energy. The LSST data will also help scientists improve the accuracy of cosmological measurements, leading to more precise estimates of the universe's age, composition, and rate of expansion. These upcoming missions will build on the data collected by previous observatories, providing a more complete picture of the universe and its most enigmatic components. Together, the Nancy Grace Roman Space Telescope and the Rubin Observatory will provide unprecedented insights into dark matter and dark energy, allowing scientists to test existing theories and develop new models for the fundamental forces that shape the cosmos. The combination of particle detectors and observatories, along with future space missions, represents a comprehensive approach to solving the mysteries of the universe. From underground experiments to space telescopes, each technology plays a unique role in exploring the properties of dark matter and dark energy. These tools not only enhance our understanding of the universe's structure and evolution but also bring us closer to answering some of the most profound questions in science. The continuing advancements in technology and observational techniques will likely lead to new discoveries in the coming decades. As these tools become more sensitive and capable, they will open new avenues of exploration, allowing scientists to probe deeper into the nature of dark matter and dark energy. Ultimately, these efforts may help unlock some of the greatest mysteries of the cosmos, reshaping our understanding of the universe and our place within it. With each new mission and experiment, we edge closer to understanding the fundamental forces that govern the cosmos. The search for dark matter and dark energy is one of the most exciting and challenging frontiers in modern science, and these tools and technologies will continue to push the boundaries of what we know about the universe. As scientists analyze the data gathered from these observatories and experiments, they will be able to refine our models of the universe and perhaps, one day, uncover the true nature of dark matter and dark energy. Dark matter and dark energy have become popular topics in science fiction, often serving as key elements that shape the narratives of various movies and books. Films like Interstellar explore the implications of space-time and gravity, offering speculative takes on how the universe might behave under the influence of dark energy. In Interstellar, the characters travel through a black hole, using the concept of gravitational time dilation to explore different regions of space. The film plays with the idea of higher dimensional beings and the mysterious forces that govern the cosmos, with dark energy hinted at in relation to the expansion of the universe. While Interstellar is not specifically about dark matter or dark energy, it touches on the themes of how unseen forces can shape the fabric of reality, pushing the boundaries of what humanity knows about space. Another movie that delves into speculative science involving dark energy is The Cloverfield Paradox. In this film, a large-scale experiment involving a particle accelerator inadvertently opens a rift between parallel universes, creating chaotic and catastrophic events. While not directly addressing dark matter, the film incorporates the idea of a hidden, unseen force affecting the character's reality in much the same way that dark energy influences the universe on a cosmic scale. The rift between universes in the Cloverfield paradox could be interpreted as a metaphor for the unknown forces, like dark energy, that govern the universe without our understanding. Books, too, have explored the concepts of dark matter and dark energy in imaginative ways. The Three-Body Problem, a science fiction novel by Liu Cixin, introduces dark matter as a central plot point. In the story, dark matter plays a critical role in the development of an advanced alien civilization. The novel explores how the manipulation of dark matter could have profound effects on technological development and the interaction between different civilizations. The Three-Body Problem presents dark matter not just as an astrophysical phenomenon but as something that influences the structure of reality itself, linking scientific ideas with philosophical musings on the nature of existence and consciousness. Dark matter and dark energy are not just physical concepts in these stories. They often symbolize the unknown aspects of the universe that science has yet to fully explain. The use of dark energy in Interstellar and the Cloverfield paradox reflects humanity's fascination with the mysteries of the cosmos. These movies offer a glimpse into how science fiction imagines the consequences of encountering forces that lie beyond our comprehension, challenging our understanding of the universe and our place within it. These speculative portrayals inspire us to think beyond the known and venture into the realms of possibility, where the boundaries between science and philosophy blur. On a deeper level, the existence of dark matter and dark energy raises profound philosophical questions about reality itself. The idea that the majority of the universe's mass and energy is invisible and undetectable by traditional means suggests that reality is much more complex and mysterious than our senses and instruments can reveal. If we cannot perceive most of the universe's contents, what does that say about the limits of human knowledge and perception? Philosophically, this can lead to questions about the nature of existence. Are we truly experiencing reality, or are we only seeing a small fragment of it? Could there be entire dimensions, forces, or entities that we are completely unaware of, yet which play a fundamental role in the structure of the universe? The dominance of unseen forces, such as dark matter and dark energy, challenges the way humanity traditionally understands reality. Historically, humans have relied on their senses and direct observation to grasp the nature of the world around them. The idea that invisible forces are shaping the cosmos without our awareness complicates this understanding. If the majority of the universe is made up of something we cannot detect or understand, how can we trust what we perceive with our senses? This realization forces a reconsideration of what it means to know something and whether absolute knowledge is even possible. The unknown nature of dark matter and dark energy also invites speculation about the connection between these forces and more metaphysical or spiritual concepts. In some philosophical circles, the existence of unseen forces has been linked to ideas about consciousness and the nature of reality. Could dark matter and dark energy be related to concepts like consciousness, which is also an invisible and difficult to define phenomenon? Just as we cannot directly perceive dark matter or dark energy, we are also limited in our understanding of consciousness, despite its undeniable impact on our experience of the world. Some thinkers suggest that these forces, which shape the cosmos in ways we cannot observe, might be connected to the deeper, intangible aspects of existence. The idea that dark matter and dark energy could be connected to consciousness or metaphysical realms suggests that the boundaries between the physical and the non-physical are not as clear-cut as we might think. Just as dark matter influences galaxies and clusters of galaxies without being directly observed, could there be non-physical forces influencing human consciousness or the collective experience of reality? If dark matter is an essential part of the universe, and if it cannot be observed directly, does that imply that there are other forms of reality that are equally hidden from us, such as mental or spiritual realms? In this context, some speculative thinkers have proposed that dark matter and dark energy could be manifestations of a deeper, universal consciousness or force that permeates everything. This idea links the physical universe with the more abstract, philosophical concepts that have been central to human thought for centuries. For example, the ancient idea of the ether in early physics, which was believed to be an invisible medium through which light traveled, was later replaced by modern theories of spacetime. Could dark matter and dark energy represent a similar kind of medium, one that connects not just the physical universe but also the consciousness of all beings within it? The philosophical implications of dark matter and dark energy are not just speculative but are also relevant to contemporary discussions in metaphysics and cosmology. The search for dark matter, with its inability to be directly observed, has led to the realization that our senses and instruments might be fundamentally limited in their ability to capture the full scope of reality. This recognition invites us to reconsider the nature of existence itself. Is there more to the universe than what we can detect with our current tools? Could the true nature of reality be hidden from us, waiting for future generations to discover? At a societal level, the exploration of dark matter and dark energy raises profound questions about humanity's place in the universe. If the majority of the universe is made up of invisible, undetectable forces, what does that mean for the future of human knowledge and exploration? It suggests that there are vast frontiers of understanding still to be uncovered, and perhaps the greatest discoveries lie in areas that are beyond our current capabilities to perceive. This realization can be both humbling and inspiring, as it challenges humanity to think beyond the boundaries of the visible world and to strive toward a deeper understanding of the cosmos and our role within it. As we continue to explore the mysteries of dark matter and dark energy, we are forced to confront the limitations of human knowledge and the possibility that much of the universe remains beyond our comprehension. This mystery is part of what makes the subject so compelling, both in the realms of science fiction and philosophy. The search for dark matter, dark energy, and the ultimate nature of reality is not just a scientific quest. It is a journey that touches on the very essence of what it means to be human and to seek understanding in an ever-expanding universe. The detection of dark matter has proven to be an immense challenge for scientists, despite years of research and numerous experimental efforts. The primary reason for the lack of direct detection is that dark matter does not interact with electromagnetic forces, meaning it doesn't emit, absorb, or reflect light. This makes it invisible to traditional telescopes and detectors that rely on detecting light or radiation. Instead, dark matter's presence is inferred through its gravitational effects on visible matter, such as galaxies and galaxy clusters. These indirect observations point to its existence, but capturing dark matter directly has been elusive. Particle detectors like those used in underground laboratories or space-based observatories search for rare interactions between dark matter particles and regular matter. However, these interactions are so weak that they occur only very infrequently, making detection extremely difficult. The sensitivity required to observe dark matter's faint effects is far beyond our current technological capabilities, which is why no direct detection has yet been achieved. In addition to this, there could be alternative explanations that we have yet to consider. Some scientists propose that the phenomena attributed to dark matter might instead be due to modifications in the laws of gravity at large scales, as suggested by theories like modified Newtonian dynamics. These theories aim to explain the observed gravitational effects in galaxies and galaxy clusters without the need for dark matter particles. However, while these theories can explain some of the data, they fail to fully account for all the observational evidence, particularly in the case of galaxy clusters and gravitational lensing. Thus, while modified gravity theories present interesting alternatives, they do not yet provide a complete solution to the dark matter mystery. It's also possible that dark matter might be made up of yet undiscovered particles with properties that we currently cannot detect or measure, and new, unexpected interactions might be at play. Another significant challenge in understanding dark matter is the integration of this concept into the larger framework of physics. The current structure of physics is built on two major pillars: quantum mechanics, which governs the behavior of subatomic particles, and general relativity, which describes the large-scale structure of space-time and gravity. Dark matter presents a unique challenge because it seems to affect gravity on a large scale, yet it does not interact with electromagnetic forces, making it a purely gravitational phenomenon. To explain dark matter within the context of physics, scientists must find a way to reconcile the principles of quantum mechanics with general relativity, particularly in the context of dark matter's role in shaping cosmic structures like galaxies and clusters. While quantum mechanics successfully describes subatomic particles, it doesn't fully account for gravity's effects on these particles in a unified way, and general relativity doesn't incorporate the behavior of quantum particles. The search for a theory of quantum gravity, which could potentially include dark matter, is a key goal in theoretical physics. However, reconciling these two theories remains one of the most difficult challenges in modern physics. The possibility that dark matter and dark energy could be the same phenomenon observed in different ways has also been proposed. Dark matter is typically understood as a form of invisible matter that interacts through gravity, while dark energy is an enigmatic force driving the accelerated expansion of the universe. Although these two concepts appear to be distinct, some theories suggest that they could be two manifestations of the same underlying entity. One such theory is the idea that dark energy could be the result of quantum fluctuations in the vacuum, affecting the fabric of space-time in a way that leads to accelerated expansion. Dark matter, in this context, might be a relic of these fluctuations, affecting the structure of galaxies and clusters in a way that is consistent with the properties of dark energy. If dark matter and dark energy are indeed related in this way, it could revolutionize our understanding of the universe and the forces that shape it, though such a theory remains speculative at this stage. When examining the cosmic evolution of dark matter and dark energy, it's essential to consider their influence on the history of the universe. Dark matter played a crucial role in the early universe, acting as a scaffolding for the formation of galaxies and galaxy clusters. Its gravitational pull helped to clump matter together, leading to the formation of the structures we observe today. Without dark matter, galaxies would not have been able to form as early or as large as they did, as there wouldn't have been enough gravitational pull to draw matter together into dense regions. This means that dark matter has been fundamental in shaping the structure of the universe from its earliest stages. In the first few 100 million years after the Big Bang, dark matter would have dominated the dynamics of the universe, dictating the formation of the first galaxies and stars. As the universe expanded, dark matter's role in the formation of cosmic structures became increasingly important, creating the gravitational framework necessary for visible matter to accumulate. In contrast, dark energy has become more influential in the later stages of cosmic evolution. While dark matter dominated the early universe, dark energy has taken over as the primary driver of the accelerated expansion observed in the current epoch. It is believed that dark energy was not as significant in the early universe because the density of matter was much higher, and the effects of gravity were stronger. However, as the universe expanded and matter became more spread out, dark energy began to dominate, pushing galaxies further apart. This shift in the balance between dark matter and dark energy has led to the current phase of cosmic acceleration. Understanding when and how this transition occurred is a key part of cosmological research. By studying the cosmic microwave background radiation and the distribution of galaxies, scientists can gain insight into how the interplay between dark matter and dark energy has shaped the universe's evolution. The question of whether dark matter and dark energy behaved differently in the early universe compared to now is an area of active research. Current models suggest that dark matter's role was crucial in the formation of cosmic structures in the early universe, while dark energy has become the dominant force in recent times, driving the accelerated expansion. However, there are still many uncertainties about the precise behavior of these forces in the early universe. For example, the exact nature of dark energy and how it evolved over time is still poorly understood. Some theories propose that dark energy was not constant over time but has evolved, perhaps growing stronger as the universe expanded. The question of whether dark matter and dark energy behaved differently in the early universe compared to now is an area of active research. Current models suggest that dark matter's role was crucial in the formation of cosmic structures in the early universe, while dark energy has become the dominant force in recent times, driving the accelerated expansion. However, there are still many uncertainties about the precise behavior of these forces in the early universe. For example, the exact nature of dark energy and how it evolved over time is still poorly understood. Some theories propose that dark energy was not constant over time but has evolved, perhaps growing stronger as the universe expanded. Others suggest that dark energy may have been present in the early universe, but its effects were masked by the overwhelming influence of matter and gravity. The discovery of more precise measurements of the universe's expansion, particularly from observations of distant supernovae and the cosmic microwave background, may provide answers to these questions in the coming years. In summary, the challenges in detecting dark matter and understanding its nature are multifaceted, ranging from technical limitations to the need for new theoretical frameworks. The potential connection between dark matter and dark energy raises fascinating possibilities but also adds to the complexity of the situation. Reconciling dark matter with the principles of quantum mechanics and general relativity is a monumental task, but it is essential for developing a complete theory of the universe. As we continue to explore the cosmic evolution of these forces, we are confronted with many open questions about their roles in the past and future of the universe. Understanding how dark matter and dark energy have shaped the universe's history and how they will continue to influence its future is crucial for our understanding of the cosmos. The interdisciplinary exploration of dark matter and dark energy opens new doors for various fields, including astrobiology. The potential indirect effects of dark matter on the habitability of planets have raised intriguing questions. While dark matter itself does not interact with ordinary matter in a way that directly affects biological processes, its gravitational influence could play a role in the formation and stability of planetary systems. The way dark matter contributes to the structure of galaxies and galaxy clusters might affect the distribution of stars and planets. For example, if dark matter has a gravitational influence on the rotation of galaxies or the movement of celestial bodies within them, it could, in theory, influence the positioning of habitable zones and star systems. A more stable environment, influenced by dark matter's gravitational effects, could potentially enhance the likelihood of life-supporting conditions on planets. Moreover, dark matter's role in the formation of galaxies and stars also indirectly impacts the conditions on planets. Stars are formed from the gravitational collapse of gas and dust, and dark matter's gravitational influence could contribute to the overall stability of a galaxy. A stable environment allows for a higher likelihood of planets forming in regions that are conducive to the development of life, especially if these planets are within the habitable zone of their host stars. However, the exact extent to which dark matter influences these processes on a planetary scale is still speculative and requires further investigation. Astrobiologists may look into how dark matter's presence in different regions of the universe could affect the probability of life arising, particularly in galaxies where dark matter density might vary. In addition to dark matter's indirect influence on planetary habitability, dark energy could also play a role in determining the time frame for intelligent civilizations to evolve. Dark energy, which is thought to be responsible for the accelerated expansion of the universe, affects the cosmic scale by driving galaxies further apart. Over time, this expansion could have significant implications for the development of intelligent life. As the universe continues to expand, galaxies will move further away from each other, and the overall density of matter in the universe will decrease. This could affect the availability of resources and the proximity of other civilizations, potentially slowing down the interaction and exchange of knowledge between intelligent life forms. The accelerated expansion driven by dark energy could also limit the amount of time that civilizations within a galaxy could coexist and communicate with one another. As the universe expands, the distance between galaxies grows, and over long periods, this might result in a cosmic isolation effect. If dark energy continues to accelerate the expansion, intelligent civilizations might face the challenge of evolving and sustaining themselves within a rapidly dispersing universe. The increasing distance between galaxies could lead to a situation where intergalactic communication becomes impossible, limiting the potential for collaborative efforts or shared technological progress. Thus, dark energy could set a cosmic time limit for the window of opportunity for civilizations to evolve and interact. Understanding dark energy's properties may also have profound implications for space travel, particularly with regard to the possibility of faster-than-light, FTL, travel. One potential avenue for FTL travel involves the manipulation of dark energy itself. Some speculative theories suggest that if we could understand dark energy and harness its effects, it might be possible to bend space-time, enabling faster-than-light travel without violating the laws of relativity. The concept of warp drives, popularized in science fiction, hinges on the idea of manipulating the fabric of space-time to create a bubble that moves faster than the speed of light. Dark energy, which is thought to be driving the expansion of the universe, could theoretically be used to create such a bubble. However, these ideas are highly theoretical and remain far beyond our current technological capabilities. Understanding dark energy's role in the expansion of the universe may provide insight into how such an ambitious goal could one day be realized. If we were able to control dark energy in the future, it could revolutionize space travel. Harnessing dark energy could potentially allow spacecraft to traverse vast distances across the cosmos in a fraction of the time it would take using conventional propulsion methods. This would drastically reduce the travel time for interstellar exploration, opening up the possibility of visiting distant star systems or even other galaxies. However, much like other cutting-edge theories in physics, the ability to manipulate dark energy for such purposes remains speculative and would require breakthroughs in both theoretical and applied physics. On the other hand, dark matter presents both risks and opportunities for interstellar exploration. While dark matter itself does not interact with ordinary matter in a way that is directly harmful, its gravitational effects on galaxies and stars could have a more indirect impact on space exploration. If dark matter is concentrated in certain regions, it might influence the trajectory of spacecraft traveling through space, making navigation more difficult. For example, dense concentrations of dark matter in certain areas of the galaxy could create gravitational anomalies that would affect the path of a spacecraft. Understanding these anomalies and how they relate to dark matter's distribution in the galaxy would be essential for long-term interstellar missions, as even small gravitational disturbances could have significant effects on a spacecraft's trajectory over long distances. However, dark matter could also present opportunities for interstellar exploration. Some scientists have suggested that dark matter could provide insights into the nature of gravity and the fundamental forces of the universe. By studying the gravitational effects of dark matter, scientists could develop more accurate models of space travel that take into account the complex gravitational fields created by both visible and invisible matter. In addition, if dark matter is composed of unknown particles, these particles could hold valuable information about the fundamental structure of the universe. Understanding the properties of dark matter might also lead to new breakthroughs in propulsion technology or energy generation, potentially providing a means to travel more efficiently across vast interstellar distances. Moreover, dark matter might offer new insights into the potential for life beyond our solar system. By studying how dark matter affects the formation and distribution of stars and planets, we could identify regions of the galaxy that are more likely to support habitable planets. For instance, understanding how dark matter interacts with the matter in galaxies might reveal areas where planetary systems are more stable and more likely to harbor life. This could be crucial for guiding future interstellar exploration missions aimed at discovering exoplanets that could potentially support life. As our understanding of dark matter and dark energy advances, it will undoubtedly have profound implications for both the future of space exploration and the search for life elsewhere in the universe. While challenges remain in directly detecting and understanding these elusive forces, their potential to shape the future of astrobiology, space travel, and the study of cosmic evolution cannot be underestimated. The exploration of these forces could lead to groundbreaking discoveries, offering new ways to explore the universe and perhaps even new ways of thinking about the very fabric of reality itself. If you like this video, then subscribe to our channel New Documentaries and hit the bell icon for more updates.